Moments of inertia, type 3, periodic time. In 2003, we were given 3 rods, each of mass m and length 2L, and they're jointed together at their ends to form a triangle PQR. The triangle is free to rotate about a fixed horizontal axis through P, which is perpendicular to its plane. So we've defined in terms of L the period of small oscillations. So the first thing we want to do is have a look at finding the moment inertia of this system, where it is rotating through the axis point P. So we have to look at the fact that each of these are 3 rods, and therefore if I'm looking at the rod PQ, I'm going to be finding the moment of inertia through its end point, which is going to be 4 over 3 ml squared. And if I look at the rod PR, it's also rotating through its end point, which would be also 4 over 3 ml squared. However, if we look at the rod PQ, well, its axis point is nowhere near the rod itself, and therefore normally if we're looking in our maths tables and we're looking at our rod formula, then we would be looking at a third ml squared through its centre. So therefore I can see that the centre and P, if I was to put a pencil on the centre point and a pencil on P, they are both parallel to each other. So we're going to have to use our parallel axis theorem. But therefore I'm also going to need to know what is the distance between P and the centre point. So we're going to start there. Okay, so if we look at the right-hand side there of that triangle PR, we know the length from P to R is 2L, and the halfway point then for QR will be L, and that's a right-angled triangle, and therefore I'm looking for this distance here, D. So basically, if I'm looking at the distance there, D, I'm going to be using Pythagoras, because I have H, O, and A. So in other words, H squared equals O squared plus A squared, Pythagoras' theorem, which is page 16 in our maths tables. And of course we have 2L squared is equal to D squared plus L squared. And therefore D squared is going to be equal to 4L squared minus L squared. In other words, D squared is equal to 3L squared. So D is equal to root 3, and the square root of L squared is L. Okay, so now we have the distance from the centre point of QR to the axis of rotation. So let's have a look now at getting our moments of inertia then. Okay. So if we look at the rod PQ and also PR through the axis of A, well, the moment of inertia through the axis point A is going to be 4 over 3 ml squared. And of course the mass of each rod is m, and the value is taken from our maths table, which is page 53 in our maths tables, okay? So the axis is at the end of the rod. Okay? So therefore for the two of those, for PQ and also for QR, we'll have those moments of inertia. Okay, so now if we're looking at the rod QR, well, as we said, through its centre, it's going to be a third ml squared because the mass is m and the rod length is 2L, so its centre point is, distance from the centre out is L. And then through the point P, well, we have to use the parallel axis theorem. So in other words, I have to get the moment of inertia through C plus md squared, because the centre is parallel to P. So it's our parallel axis theorem. And again, this is page 53 in our maths tables also. So therefore, if I work out the total moment of inertia it's a third ml squared plus the mass times d squared. Now if I go back, d squared was 3l squared. So if I combine those two together, the moment of inertia through P, sorry, I'm just looking up there, that should also say P as well, is going to be 10 over 3 ml squared. So therefore for the system, so the three rods making our triangle, the moment of inertia through P is going to be 4 over 3 ml squared for PQ, 4 over 3 ml squared for Q or for P or, and 10 over 3 ml squared for the rod Q or. So together the total moment of inertia for the system is 6 ml squared. So of course you can do all of that in one go if you want to speed up your time, and there was 5 marks going for that then in the exam. So if we're looking at the next part of our question, well, we have to find the period of small oscillation. So the reason we always have to start with a moment of inertia is because we need that for the rest of our question, whether it be at angular velocity or a period of small oscillations. So if we're looking at the period of small oscillations, we know our formula is t is equal to 2 pi times the square root of I over mgh. So of course I need to work out what is my h, what is my distance. So I'm going to draw a new diagram for this. So of course we have P, which is where we're rotating through. And if I'm looking at the centre of gravity of my system, well, centre of gravity is median. So if I get the midpoint to the opposite vertex, I'm getting my median. Midpoint to my opposite vertex, I'm getting the median. And the point of intersection of our medians is, of course, our centre of gravity. Or in other words, our centroid. And of course, we have to remember from higher level maths that our centroid, what does it do? Well, it divides the medians into the ratio of 2:1. So therefore, this is going to be 2/3 of the distance down. This will be 1/3 of the distance down. Remembering, if we go back to that previous diagram, that I had called that line from P to the midpoint of Q or was D. So therefore, the ratio 2:1 means that it is 2/3 of the way down for the centroid, or the centre of gravity. Okay, and therefore this is h, the distance from the centre of gravity to our axis point in our period of small oscillations formula. So in other words, t is equal to 2 pi times the square root of I over mgh. So our h is going to be 2/3 of d. And of course, our period for small oscillations is on page 54 in our maths tables. So for our compound pendulum. So if we sub in our values, we have 2 pi times the square root of I, we've worked out to be we've worked out to be 6 ml squared. The mass is of the system, not just the one rod. So we have m for P, Q, and m for P or, and m for Q or. So the mass of the system is 3m times g. So in other words, our weight through the system is 3mg. And of course then h is 2/3 of d. But of course d, we said, was root 3l. is root 3L. So therefore, if I sub that in, we have 6ml squared over 3mg times 2/3 root 3L. And now all I need to do is tidy that up, and that gives me 2 pi over the square root of root 3L over G. And we were getting 5 marks for setting up our period of small oscillations and 5 marks for simplifying. Okay, so for the next part, to find in terms of L, the length of the equivalent simple pendulum. So we're still on page 54 of our maths tables, and we find for the simple pendulum, our period is given by 2 pi over the square root of L over G. So as not to confuse between the compound pendulum length, I'm going to use a capital L for our simple pendulum length. Okay, and again, page 54 of our maths tables. And then by equating them, so we're going to equate our simple and our compound pendulum. So we end up with 2 pi square root of capital L over G is equal to 2 pi square root of root 3L over G. So small l for our compound pendulum, because that's the way it was given in our question. So our root 2's are going to divide in evenly. And then if I square both sides, I can get rid of my square root. So I have capital L over G is equal to root 3L over G. And of course then my G's are gone, so G goes into G once, and that leaves me with the simple pendulum's length must be equal to root 3 times the length of the compound pendulum to have the same period. So again, 5 for equating and 5 for getting out our answers. So we had 5, 10, 15, 20, 25. Oh, yeah, sorry, we had 5 for setting up our H there as well. So 5 marks for saying that H was equal to 2/3 root 3L. Okay, so we had 30 marks total for this question. Okay, so nice little periodic time question there.